-1. All right, hi, welcome back to Math 234. I am still your host, Steve Dragoo, and this one's gonna be a little bit different. So first off, we're doing section 16.6 in the middle of chapter 14. So we're jumping ahead a bit to look at something out of a later chapter. But also it's a little bit different because I'm not actually recording this in front of a classroom full of people right now, but instead I'm in my office by myself. And generally, at least once per lecture, I make at least one weird arithmetic mistake that comes out of nowhere because I'm just not very good with numbers, and I won't have anyone to catch me this time. So if you're watching this video after the fact and you catch whatever weird, dumb mistake I've made, maybe, I don't know, reach out on Piazza might be a good way to do that, to let me know what happened, or I suppose you could just tell me in lecture the next time you see me there. Uh, I'll probably know by then. But anyway, we're gonna give it our best shot. Recording here all on my lonesome. So, without too much further ado, let's look at chapter 16.6. In particular, in this chapter, we're looking at parametric surfaces. Before we dive too far in, I want to acknowledge we've already looked at parameterizations once already. This is our second time getting into parametric things, right? We've been calling them just parameterizations in general, but there is going to be a difference between the two times we looked at parameterizations, because the first time we looked at parametric curves, and this time we're going to be looking at parametric surfaces. I want to start by sort of clearly establishing the difference between the two kinds of parameterizations we're doing. When we were looking at curves, those are a curved line, but importantly, they are a one-dimensional object that's existing in three space. So I've got just a line and it might be curving through three space, but it's still just one line. It's got one dimension, which means I can describe the entire shape using only one parameter. This time we're going to be describing parametric surfaces. So we're going to be rewriting X, Y, and Z in terms of parametric equations, but a surface is going to be a two-dimensional object. So think of like a thin object or maybe like a curved plane because it can exist in three space, but again, it won't have any thickness to it. It'll only have two dimensions, which means I only need two parameters to describe the object. When we did our original run at parameterizations, we almost always used t as our parameter. So we're going to look near in the alphabet to grab our new parameter for doing surfaces and use S and T, the first two letters of Steve. Coincidence? Well, when you see the other two parameters we use being U and V, maybe you'll be convinced more one way or the other. Maybe that's not helpful at all. Again, let me know somewhere. I really should be doing this in front of people. Oh well. So we might use S and T, we might use U and V. Both will work for our parameters. We might even use R and theta because those are perfectly valid parameters as well. But I digress. Let's come look at the first couple of examples from the pre-class video. So, trying to describe this torus here, uh, because it's a just the surface of the torus. So we're not describing the part through the middle of this donut shape that we're looking at, by the way. And if you're looking for the mathematical term for a donut, it would be a torus. That's this thing. And since we're only describing its outer surface, we aren't describing the interior of the donut. And by the interior, I mean the part that's inside the donut, not the donut hole. But we aren't trying to describe that interior, right? If we looked at the full three-dimensional shape on display here, we'd call that thing a solid because it would have volume. But we aren't looking to describe the volume. We're only trying to talk about the surface, so the exterior of this donut. So because it's only the surface, it's thin, has no thickness, I'll only need the two parameters to talk about it since I'm effectively describing an area. It might be a surface area, but it's still a some kind of an area thing that I'm doing. So again, only the two parameters need to get involved. We're told that we have this parametric set of equations. We also have the implicit function listed above that, but that's, well, that can be a bit of a bear. So instead of trying to use that implicit surface, which isn't that nice looking of an equation, we'll instead use these parametric equations because we think that they'll be easier to use in some way. Also, generally, if we go to a parametric equation, we won't have to worry about things like plus or minus, leading us down two separate branching functions. An ideal parameterization will be just a single set of functions. So I don't need to go through like branching paths and piecewise functions and all that. Parameterizations are hopefully there to avoid all of that kind of stuff. In fact, all of the nice parameterizations we'll look at in this course all will be functions. But if I'm looking at the parameterizations I've chosen, it looks like our parameters are u and v, and both of them are being used as angles. You can tell they're being used as angles because all of my parameters keep getting plugged into sine and cosine. So I want to think about parameters in this example as angles. In particular, I see a cosine u stuck to the x, a sine u stuck to the y, and then u doesn't show up at all in z. So I'm thinking u is probably going to look a lot like theta from our polar coordinates. Then that leaves the other angle. If I'm looking through those same patterns for how I see the v parameter showing up, starts to look like maybe this has some similarities to phi out of spherical coordinates. It's not exactly one-to-one there because I don't think I'm measuring this angle from the z-axis. But instead, I think I'm going to use it to measure around a cross section of this donut, try to cut out a circle from the middle. Looks like phi might be going around that, whereas theta is traveling all the way around the big donut. So in particular, if I'm looking at the orange line that I've drawn in, I think that that's taking me as a trip all the way around the u parameter, which again, I want to be thinking of as theta. Right? That orange line is taking me all the way around theta, where the pink or magenta line I've drawn in is taking me one trip around phi. Those are the two sort of axes or the two spots where I'm going to think to see the unit circles show up for u and for v. But in particular, those two traces that I drew in, or parametric curves, are v equals 0 and u equals 0. So just looking at what would happen if I fixed my two angles at their starting values, or each angle at its starting value, and just looked at how the other one operated around this donut shape. So plugging that in, those are the equations that I got. And another quick word before we dive into the meat of what we're doing is going to be to look at some very similarly worded questions, but that are going to have different parameterizations. So for all three of the next examples, we're going to look at a cone and a sphere, and the same cone and the same sphere, but changing slightly what we're asking for. Because in the first example, we're going to ask to parameterize the cone. So the parametric equations I come up with should describe the cone, whereas in the second two, we're looking to parameterize the sphere. So it should be the sphere that gets the parametric equations. We're going to use the other object that's there to sort of limit ourselves. We're going to use that to figure out what our bounds ought to be. But when we actually go to parameterize the object, we need to make sure that our parametric equations match the object we're supposed to parameterize and not the boundary object. So in particular, the first one, we want the portion of the cone that's inside of the sphere. So if you're imagining this thing is an ice cream cone, where we've got a scoop that's sitting on top, and the cone part of our cone is really buried on the inside of that sphere. It's currently underneath the ice cream, but if you can imagine that cone keeps going down, that's the part that I want to parameterize. So I found that thinking about cylindrical coordinates is pretty nice for parameterizing cones. So the two options for r and theta, or my two parameters, s and t, should match up to r and theta. And then in cylindrical coordinates, a cone is usually given by an equation that something like r equals z. And that's in fact exactly what we found over here. So the parametric equations for the cone, again, look like something out of cylindrical coordinates, versus if I wanted to parameterize the sphere, I'm going to choose something that looks a lot more akin to spherical coordinates. Easiest way to parameterize a sphere is going to be with spherical coordinates. But then it's the intersection that determines the bounds for my parameters. Because when we set up these parameterizations, the domain in which our parameters are allowed to exist in are going to end up being pretty important. That's often how we figure out what bounds to set for the parameters. Now, theta is usually pretty nice. Most of the time, we're just going to go 0 to 2 pi for our theta surrogate, as long as we're going all the way around, which often we do. And then the other parameter might be limited in a different way. So here, since we're using s as our stand-in for r, we're using s as stand-in for the radius, I need to find the radius value when the sphere and the cone intersect. That's what I did right here was found the intersection of the sphere and the cone. So I'm just plugging one equation into the other. And I found that that's at an r value of square root 2 or a z value of square root 2 since r and z are equal to each other on that cone. So we can look back up at the cone and kind of see that curve of intersection showing up. It's kind of like right there. That's our curve of intersection for figuring out our bounds. But then when we switch that over to spherical coordinates, it's not the radius that we need to find a boundary for, but instead our phi surrogate angle, so the angle that isn't theta. And we found that those two objects, the cone and the sphere, intersect at an angle of phi equals pi over 4, which when I switched over to my spherical coordinate parameterization, I'm still using t for theta because t and theta work out nicely like that. But I'm going to use s as sort of that phi-like surrogate, that phi-like stand-in. So I found that those things intersected again at an angle of pi over 4 is where the cone and the sphere intersect. And then I need my two parameterizations to first get the part of the sphere that is above the cone, and second, get the part of the sphere that is below the cone. So the part that's above, remember that an angle of 0 radians for phi points straight up the z-axis. So the above the cone part is from 0 to pi over 4. And then below the cone is from pi over 4 all the way down to the bottom z-axis, which is an angle of pi. So recall that our default choices from spherical coordinates were 0 to pi for theta, but only 0 to 1 pi for phi. So that blue angle, we only wanted to have a max. Our standard choices, our default choices would have been 0 to pi. And then again, we're cutting that up to have a top part and a bottom part. But enough of generalities. Let's go solve an equation. So parametric surface time. I'm assuming that peanut butter jelly time is an older meme that checks out at this point. If you haven't seen it and you appreciate Ryan's sense of humor, feel free to Google that. I'm sure it'll be the first thing you find. But again, I said that I was going to actually get into doing some of this stuff, so let me try to stay on task. So we want to find a parameterization for the surface z equals 3 square root of x squared plus y squared. Now, when I see that equation, two things come to mind. First thing is looking at that x squared plus y squared that's on the inside of a square root. Anytime I see something like that, I'm starting to think about polar coordinates. So I think that x squared plus y squared looks an awful lot like polar. So I'm already going to start thinking about that as a likely choice for my parameterization. Maybe I'm going to go cylindrical coordinates. Maybe I'm going to go spherical coordinates. Don't know exactly yet, but I'm seeing some things that are making me think polar. The next thing that I'm thinking about is that entire equation, because it's one that we've seen before. In particular, from back in chapter, or rather section 12.6, which was all of our quadratic surfaces, we know that this thing is a cone. Or in maybe slightly easier is to think of z equals just square root of x squared plus y squared as a cone. So again, when you're trying to classify those shapes, it's often easier to just ignore all of the numbers. So just pretend all the coefficients are either 1, -1, or 0, and identify your shape that way, and then build back out to whatever specific equation or specific shape you need. Because I can just take a cone and then stretch it out by some factor of 3, because I can see I've got a factor of 3 here, but still knowing that it's a cone is my first step. So whatever I can do to easily get that idea together, it's going to be nice. So if I'm thinking this is going to be polar coordinates, then I really want to have r squared equal to x squared plus y squared. That was the big thing that set me off, thinking that I should be trying polar coordinates. So I'm going to do that first. I meant to write let's try there. Cool. So let's try r squared equals x squared plus y squared. But because my two parameters are going to be s and t, and I usually like to reserve t for theta because it just helps my brain out that way, right? T theta. I'm going to use s as my radius stand-in. So I'm going to have s squared equals x squared plus y squared. But again, I'm really just thinking that that's a polar coordinate. But I'm changing my parameters to fit the request of the problem. So that means I'll also have x equals r cosine theta and y equals r sine theta. R sine. Managed to write down the thing that I was saying, even though I'm thinking something else. Because again, I'll just replace r with s and theta with t. So s cosine t and s sine t. Now, that means my equation, which was z is equal to 3 times the square root of x squared plus y squared. I really want to call that thing z equals 3 times the square root of s squared. Right? Because I really wanted to make that substitution, meaning I'm ultimately going to use the equation z equals 3s. Again, that's coming in from the way that I wanted to define my polar parameterizations. So with that, I think I'm ready to just at least write down my parametric equation part. So I think I've got it all together now. So my cone, which is going to be r of s and t, some parametric equation where the parameters are s and t, looks like s cosine t, s sine t, and 3s. And then I'll add some color back in here to keep our parameters straight. I've been using blue for s and green for t, so I'll keep doing that to try and keep those straight. So that is the big part of finding a parameterization. If I'm going to split it into halves, this is the bigger half. Of course, if you're paying attention to what halves are, shouldn't be a bigger half, and a small half implies that they're equal, but I digress again. Staying on task, I found the parameterization. I found the parametric equations, which again is half of the parameterization. I also need the bounds for my parameters. Now, t, I know I'm going all the way around. I didn't have any reason to cut t in half anywhere. So I'm just going to stick with 0 to 2 pi. Again, unless I have a reason to not go all the way around, I'm just going to assume t is 0 to 2 pi. If I am going to look at cutting out part of spinning all the way around whatever my object is, like if I wanted to only go halfway around the cone for some reason, or maybe I wanted the part of this surface that lies specifically in the first octant, then I might start thinking about limiting theta. But if I don't see anything that should suggest to cut this, revolving shape off somewhere, 0 to 2 pi is my default choice for theta. So I'm just going to work with that until I need to change it up. Now, S is the other one we got to figure out. We need bounds for the radius stand-in. And if I head back up to what I know about Z, I was told in the start of the problem that Z exists only between 0 and 3. And I also just found that Z is equal to 3S. So if Z needs to sit between 0 and 3, that means that S needs to sit in the interval 0 to 1. So if I just divide that interval by 3, 0 over 3 is 0, 3 over 3 is 1. So that's my full parameterization. It includes both the parametric equations and the bounds for my parameters. All right, our next equation, our next example, which is going to be another parameterization. This time, we're after x squared plus y squared plus z squared equals 9. And again, going back to what I know from section 12.6, where we did quadratic surfaces, we know this thing's a sphere. You probably didn't even need to go back to that set specifically. Equations of spheres are pretty common. You might have just known this was a sphere right away. So if I've got a sphere, I know its radius is going to be 3. That element's going to be fixed, but I should also be thinking about spherical coordinates. So I believe that spherical coordinates is going to be the easiest way to parameterize a sphere. Coordinates. There we go. So in spherical coordinates, what are our usual parameters? Well, we've got rho and theta and phi. In this particular case, rho is just 3 because I'm only parameterizing the surface of the sphere. I'm not trying to get its interior. I don't want to parameterize a solid sphere. I just want its surface. So rho is going to be 3. But then for the other two angles, they'll be my two parameters. So I'll keep using t for theta, which means I'm going to have s for phi. So if I just jump over to those spherical equations, x I know is rho sine phi cosine theta. Y is rho sine phi times sine theta, and z rho cosine phi. So remember that rho sine phi that shows up in both x and y is really just what the polar r looks like, but in spherical coordinates. So the same r that we would have used in cylindrical coordinates, that r value, it becomes rho sine phi if I switch over to thinking about spherical coordinates. So just multiplying that r into both sine and cosine for y and for x respectively. So then z is the other part on that phi angle. So z is going to be rho times cosine phi. So those were my 3 equations from spherical coordinates. So I just want to use that as my base for my parameterization. And let's add a color to the object. How about purple for spheres? R of S and T is going to be the parametric equation 3 sine S cosine T 3 sine S sine t, and 3 cosine S. Again, I'll add some color back into this for clarity. Oops, I missed an S. That'll be in blue and green for theta. Theta only showing up for x and for y. It's not over in the z variable, or the z parametric equation, I suppose. So again, those are our parametric equations, but the parameterization is not done until you have bounds for those parameters. So t, which is our theta, is 0 to 2 pi, and s, which is our phi, is in 0 to pi. So the note down at the bottom of the screen currently, if you're doing things right, then often your bounds for your independent variables or your independent parameters shouldn't depend on each other. Right? Most of the time when we put these parameterizations together, our two parameters will be independent of each other, as when we're typically constructing an x, y, z space, x, y, and z are all independent parameters, or oftentimes they are. Particularly if we've got a function that's z is a function of x and y, then the parameters x and y are independent of each other frequently. It's not always the case, but it's nice when it works out that way. All right, and now everything we've done so far is really just an extension off of parameterization, which we already did back in chapter 13. This is the section where we're going to dip a toe ever so slightly into chapter 16. So once we hit chapter 16, things tend to get hairy fast. Chapter 16 can be quite a challenge. In particular, we've got some rather insane theorems that will resolve eventually, but kind of what I tend to hear from people is that Green's theorem and Stokes' theorem and the divergence theorem, being the three things that we're going to look at in chapter 16, finally start making sense about the third time you see Calc 3, which means you take it once as a student, then maybe it comes up again in an engineering course, and then finally by the time you're trying to teach someone Green's theorem, you're like, oh, okay, it clicks. But just as a forewarning, we're going to hit some rather difficult sections near the end of the course. So in order to hope that things don't go as bad as possible at the end, we're going to introduce a few concepts early. One of which is a building block to help us with surface integrals, which is this sort of terrifying looking integral with two integral signs that you've seen on the screen in front of you. This is the surface integral of some vector valued function f, dotted with its normal, or dotted with a normal vector to the surface s. And then ds, our differential, or the integration token that we've got to spend in order to integrate that thing, is just an infinitesimal little change along our surface. But the part that we are going to focus on, that doesn't require us knowing double or surface integrals yet, is the normal vector. So finding normal vectors to surfaces, because we can do that now. We know how to find normal vectors. We've been doing a bunch with normal vectors. In fact, we just did a whole set on tangent planes, which is very strongly tied into normal vectors. So we're going to look at normal vectors for these surfaces now, so that hopefully when we get to trying to do surface integrals, we can say, okay, we've got a little bit of a foothold on the normal vector part. Let's look at the double integral part of this surface integral. So the thing we're going to focus on for the rest of our parameterizations, and the examples we're doing right now, is also finding their normal vectors, because again, we'll be needing those later. So again, sort of ignore that surface integral that was above, except for the part where we're looking for a normal vector, n, highlighted in red. What are they going to look like? Well, we already know how to find normal vectors sometimes, because we've had some luck just finding some tangent vectors and taking their cross product to find a normal vector, right? If I have, two tangent vectors, maybe that lie in a plane, two vectors in there, I can take the cross product to get the normal vector. Or when I was looking at two curves that intersected back in chapter 13, I think we said we could find a normal vector by taking their cross product. Or maybe I'm making that up because it would be great to have a live studio audience to let me know that I'm totally off base, but well. That said, normal vectors, they're going to be the cross product of two tangent vectors. So if I am on my surface, I can find two different tangent vectors at some point. I can take their cross product to get a normal vector. So that's what we're going to do with our parameterizations, because I'll have two parameters that make up the surface parameterization. So I can get two partial derivatives, one with respect to each parameter, take their cross products, and find a normal vector on my surface. So let's go do that right over here. Starting with this parameterization, which we are being told parameterizes the paraboloid over on the right. So that's, in particular, it's an elliptical paraboloid. It's opening down, and it looks like it's been shifted up 5 units based on that z component at the end there. Right? Z is at 5 minus u squared. And the first thing that we're going to try to do is a parameterization for the boundary curve of S. So the boundary curve of our surface over here. If I go to look at the boundary curve, which again, when you hear curve, we should be thinking about a line, right? So this is just probably a curved line going through space, but again, should be just a line and not a surface. So finding a boundary curve, I'm just looking at the object. I think it should probably be this shape right here, right? Right along the edge of my shape, the boundary of the shape. It's that curved line where the thing opens up and then stops because we're being told one of our parameters is only between 0 and 2. So that curved line, that'll be my boundary curve that I am going to try to find. And if I'm looking at sort of the shape that's here, maybe I'm going to look up at the top and see that that's at a z value of 5. Right? Sort of the vertex of this paraboloid is at 5. And that's going to correspond to a u value of 0. Versus if I look at the boundary curve that's down at the bottom, which is at z equals 1, that's going to be at a u value of 2. Since I know that z, or the parametric equation for z, is equal to 5 minus u squared. So if I'm looking for my boundary curve, I think that's going to be at a parameter value of u equals 2, right? And also I can see that u exists between 0 and 2, so I would probably expect my boundary to be at one of those two values. Probably not at any value for the theta stand-in. In this case, it looks like v is going to be our theta stand-in because it's just spinning all the way around the circle. I don't think theta is going to be deciding my boundary curve. I think it's going to be the parameter that I still have in my boundary curve. Because again, as we're thinking about getting these things to their parametric curves, that means I should only have one parameter. It's a curved line. It's a one-dimensional object. I'm expecting only one parameter on a curve. And that's because I'm going to replace one of my parameters with a constant. In this case, it's going to be u will be the constant value of 2, and v is still hanging out. So if I do that, this boundary curve should just be r of u and v, but with 2 plugged in for u. So I think that's going to be 2 times cosine v, 2 times the sine of v, sine of v. Try my best to make sharp edges on those v's because u's and v's tend to look a lot alike, particularly in handwriting. And finally, 5 minus 2 squared is going to be 1. And I really, really hope I did that math right, because again, this is be the great spot where my live studio audience would catch some sort of awkward arithmetic mistake that I would have made, because that seems like about the next most likely spot where it would happen. Cool. So there's my boundary curve. Again, I'm only expecting to see a single parameter in a curve, since it's just a one-dimensional object. So up next, we want to find an upward normal vector of our surface at some specific parameter values. So if I just kind of maybe say that that point is about here, I'm looking for that normal vector right here. Let's give it a name. We'll call it n. So you often use n for normal vector. So we saw earlier that if I want a normal vector, I should take the cross product of two tangent vectors. Anytime we hear tangent or think about a tangent vector, we know we should be thinking about derivatives, because derivatives and tangent lines, tangent vectors, tangent planes, all of those are very strongly tied together. So I should be thinking, all right, I need some partial derivatives. So since that's my first idea, I'm going to do it first. I'll come back to some of my other ideas in a moment. So I need a partial derivative of that parametric surface, starting with a u partial. This looks like 1 cosine v, 1 times sine v, and negative 2u. While I'm here, I might as well also get the v partial. Use orange for v. I don't know. I just like orange for some reason today. It's actually kind of been a this semester thing. I've been sort of into orange. I don't know why. Is that relevant to the topic at hand? I don't think so. But I need to do something to distract myself while I try to do some math. Uh, Maybe I should have been talking about what I was doing. I took my v partial, uh, which meant that I'm taking the derivative of the two trig functions, leaving u constant. The derivative of cosine was negative sine, and the derivative of sine is cosine. And because the z element, the z component, has no dependency on the angle v, its partial is going to be 0. Anyway, I should now go plug in my parameters to those two vectors. I suppose I could take their cross products before plugging in the parameters. There's no reason I couldn't. The equation would just get a little messy. And since I know I'm evaluating at a point, I might as well plug in early and save myself a little bit of a headache. So I am looking for R partial U evaluated at 1 pi over 2. And it is going to give me the vector. Well, cosine of pi over 2 is 0. Sine of pi over 2 is 1. And negative 2 times 1 is negative 2. And then for my v partial, again, being evaluated at parameter values of 1 and pi over 2, I am going to get, this looks like negative 1, since sine of pi over 2 is 1, 0, cosine of 0 is pi over 2 is 0, and still a 0 in the end. And then I know I want that normal vector, so I'm going to take a cross product of these two guys right here. So I, J, K, 0, 0, 1, negative 2, negative 1, 0, 0. And I'm going to end up with a vector that looks like the following. 0 minus 0 is 0. For my y component, -2 times -1 is 2, minus 0 is 2. And then 0 minus -1 is 1. So I have found a normal vector. And that's what this guy is here right now. So we need to talk about one last element before we end up with our choice, because we were told we needed to go find the upward pointing normal vector. We haven't really discussed what upward means yet. So probably a decent time to do that is right now. I'm going to slide this over so I've got a little more space to work over on the left side. And also I am going to don't need my arrow to be that long anymore. So upward, what does that mean? Because it was over in our definition. We didn't just need any normal vector, we needed the upward normal vector. Well, thinking about what that might mean for a vector, we define z to be our upward direction here, or z to be the axis that deals with up and down. So if I want to find a vector that points upward, I just need the z component to be positive. The x and the y components shouldn't matter for a vector being upward or downward, only the z component matters. So I'm looking for an upward pointing normal vector. I need to make sure that the z component is positive and nothing else matters. Conversely, if I wanted a downward pointing normal vector, same kind of thoughts apply, but this time I want a negative z value in that vector. So again, the z-axis will deal with up and down. So positive z is upward and negative z is down. So over here, I really meant to write in, this was r partial u cross r partial b. So it's usually a good idea to label what it is I'm doing. It generally seems like a decent idea, particularly if anybody's going to try to come back through and read my notes later. And what I really know is that this cross product, or u cross rb, which I know I wanted to say is a normal vector, I should probably add a plus or a minus here to deal with the fact that when I get the normal vector in the end, it might be pointing up or it might be pointing down. I won't really know until I multiply it all out. But I know that once I do, I want to make sure I select a vector that points up, which means that when I get my vector at the end here, I really want to be thinking about a plus or minus on that vector. Now this one, since it's got a positive 1 there on the end, I already had the upward pointing normal vector. So I didn't need to change anything here. But if that number were negative for some reason, as I think we'll see in a later example, I'll just multiply my entire vector by a negative to get the upward pointing one. But again, it's the thing I'm focusing on is just that z component. If my z component is negative, when I take the cross product, I'll just multiply the entire vector by -1 to get a vector that points up instead. But all right, now that we did all of that, let's go find the equation of the tangent plane to our surface at the point that we've already been looking at. So parameter values of 1 and pi over 2. So I'm missing just one part here. I never actually calculated the point itself. I never plugged 1 and pi over 2 into the original parameterization R. So I'm going to do that next. If I plug those values in, well, x was the cosine of v, so cosine of pi over 2 is 0. y was the sine of pi over 2, which is 1, and then 1 times u, which is also 1, is 1. And finally, for z, 5 minus u squared, if u is 1, that's going to be 4. And I'll bring back in my normal vector, which I had just calculated above. It was 0, 2, 1. Now I've got a point and a normal vector, and that's all I need to create the equation of a plane. So I know that I want this thing to be a tangent plane. So I could go look at equations for tangent planes like we just did in the previous section, 14.4. But since I already have the normal vector for the plane, which is not usually how we found tangent planes in the last section, and it kind of is, but we had a more formulaic approach. Since I've already got my normal vector this time, I'm just going to go back to the basic definition for planes. Whereas if I have a normal vector A, B, C, I can just plug it right in. So what I want to do, highlight, I'm using red for normal vectors, so I'm going to keep doing that. Highlight that normal vector and with some red brackets. The equation of my plane, I think, is going to look like the following. 0 times x minus 0 plus 2, I almost said 1, times x minus 1 plus 1 times x minus 4, z minus 4. Well, at least I caught myself this time. Z minus 4. And before you go post on Piazza about that, yes, I did catch that I put an X twice, or well, 2.5 times, because I said it the third time too. But again, caught it before I could get corrected later on. Well, sort of knew that'd be happening. Oh, but right, to keep emphasizing what's going on, I think that we can use the color red to tie together how that normal vector is playing into the equation of a plane. So let me just also come in and highlight where each of the numbers on the inside of the parentheses are coming from, because those are each just from a point that is on the plane. And I found the point I wanted to be tangent to. So I'm going to plug that point in for the equation into the equation of a plane as well. Plugging each of those guys in, that's how I ended up with that equation. I could simplify that a bit, right? Multiply everything by 0, maybe gather up all my constant terms. But I think that this form makes it a lot easier to actually see how the plane was constructed. So I'm going to leave it there for educational purposes, since I guess that's my job or whatever. Uh, anyway, this is the last example. So let's do that and get out of here. We are going to parameterize the cylinder over on the right. It's got the equation x squared plus z squared equals 9. And we're also told that x is going to exist between 0 and 2. So find a parameterization for that surface. All right. I think we can pull that off. Again, when I see an x squared plus y squared, or maybe a y squared plus z squared, or maybe a z squared plus x squared, two of the x, y, and z variables squared and added together, I am immediately going to be thinking about polar coordinates. So think polar again. But this time, instead of x and y as my two polar coordinates, or the two original variables that I'm going to transfer over, I'm going to use y and z. Or rather, the problem was using y and z. I'm just going to adapt polar coordinates to fit those. One of them needs to be cosine theta. The other one needs to be sine theta. And it can be a bit of a free choice as to which one goes where. I tend to put, thinking about, the order X, Y, Z, X, Y, Z, X, Y, Z, I tend to put the first one as cosine and the second one as sine. So for X and Y, X is cosine, Y is sine. For Y and Z, I tend to do Y cosine, Z sine. But then for Z and X, because I want my pattern to loop around, I'll use cosine for z and then sine for x. None of that is a very specific thing or something that you have to do, and just choose to do it that way so that I have some sort of order for what I'm doing. But I'm also going to pay attention to this x needs to be stuck in 0 to 2. Because if I'm thinking about the polar coordinates or the polar parameters that I'm using right now, I only needed theta to describe y squared plus z squared equals 9, right? That's just the one circle. It's like the circular base for this cylinder that looks to be expanding all parallel to the x-axis. So only needed one parameter to do y and z, which means I've got my other parameter free for x. And in fact, because this thing is a cylinder, it's almost so simple that you don't even see the solution. So for my parameterization, which is going to be r of s and t, also r, s, and t, look, those are all alphabetical. But I digress again. Again, I said that x was so simple, you might not even notice it. I'm just going to use s for x. If I have a cylinder, that usually means that one of my variables isn't present in the x, y, and z equation that we have for the surface. Oftentimes, that missing variable is just going to get its own parameter and it won't interact with anything else, which is kind of the design of cylinders. So S for X, because what else am I going to use? And then I came up with my two parameterizations for Y and Z. 3 cosine t for Y and 3 sine t for Z. Again, I'll be using t instead of theta. But again, my parameterization is not complete until I give it bounds. So S, because it's just the X surrogate, is between 0 and 2. I was just told that in the problem. It's also that thing that's highlighted in blue at the top of the screen. T then, it's our theta stand-in. Unless I have reason to think otherwise, I'm just going to set 0 to 2 pi as my bounds. Even when I do have reasons to think otherwise, I still start from 0 to 2 pi, and then I'll just delete pieces as I need to. So I've got my parameterization now. What are we going to do with it? Well, just like the last one, we're going to look for a parameterization of the boundary curves of the surface, if we have any. And here, I think we've got two of them. So one of them is right here on this front face, and we're going to see how well I can do it tracing an ellipse around this cylinder. Oh, I had ink to shape turned on, so that's kind of cheating. But since it just happened anyway, I might as well fit it nicely to the shape that I have. Yeah, I don't know. I like to get enough. I've got this boundary curve at x equals 2. That's my front face. I've also got the boundary curve that's over on its right edge, or maybe its back edge. Oh, I was doing so well right at the beginning, and then I just got distracted and didn't really finish the job. Also, I noticed how bad this other cylinder got, so I'm gonna try to fix it again too. Okay, perfect's the enemy of good here, Steve. Just let it go. Okay, ta-da, boundary curves. They're there. I can also, I suppose, trace along the back edge with a dotted line. That second boundary curve is going to be along x equals 0. So when I go to create my parameterizations for boundary curves, again, I think I've got two of them. One is at x equals 0, and one is at x equals 2. And both of these I'm going to set equal to the s parameter, because that's what x was. So for my first boundary curve, R1 of just t, it's a curve, so I should only be using one parameter. It's really just the original parameterization. but plugging in 0 for S and leaving T as T. So if I do that, I'm going to get, let's fix those braces a bit. There we go. 0. 3 cosine T, 3 sine T. And then for my second boundary curve, I'm going to use some technological magic to copy and paste my answer and change a few things. First off, I'm not plugging in 0 anymore, and also this isn't R1, but this is instead R2. But I think that my second boundary curve is going to look pretty similar, since the only thing that's changing between these two boundary curves is the S parameter. T still gets to run free and do as it pleases, right? It spins around in its circle because it's standing in for theta. But instead of 0 for S, I'm going to use 2 for S. Which means in the parameterization, the only bit that changes is the X coordinate or the X component. And then both my Y and Z elements get to run free. They don't change. Well, they do change, but they don't change from R1. They're in fact the only things that change because they're not constant. They still have variables in them. I'm probably explaining that more than I'm supposed to. All right, this is oh no, there's two parts left. I was gonna be like, oh, last part, home free, but no, we got to do two parts of it here. So C is gonna ask us for an equation for the outward normal vector to the surface. Notice how it's not asking for the outward normal at a point this time, though, which means we are instead going to find some sort of function for an outward pointing normal. But the process is still going to be the same. We're going to take some partial derivatives. In this case, r partial u I'll do first, r partial u, or partial s. Where in the heck did I get u from? Tired or something. Anyway, r partial s, I need a derivative of the parameterization. So I'll pull that back on screen there at the top. Well, the derivative of s is 1. Well, then both 3 cosine t and 3 sine t have no dependency on the s parameter, which means their partial derivatives with respect to s are going to both be 0. Then if I go look at r partial t, so the theta derivative, or the theta partial, well, this time it's the x component that has no dependency on the angle, but each of the other two guys get some derivatives. It looks like -3 sine t and 3 cosine t. And where previously I would have plugged in a point to find specific tangent vectors, these I'm going to leave as their general equation. General equation. And come down here and take a cross product of those two partials. One of those was for S, one of those was for T, and I set up a cross product calculation matrix. I'm gonna need this one to be a little wide because I've got to put some functions in here. Let's see, -3 sine t and +3 cosine t in right there and close the thing off. Maybe slide these two bits over a little bit so they still look kind of centered. And take a cross product. Well, for the x component, I get 0 minus 0 is 0. For the y component, looks like I'll have 0 minus 3 cosine t. And for the z component, I'll get -3 sine t minus 0. Now, back to what we had discussed previously when we had our upward versus downward argument discussion, whatever we're going to call that. And by we, I mean I'm talking to myself here. That, that wasn't necessary. Focus. Sorry for yelling into the microphone. We're going to put a plus or minus on this normal vector. So again, when I came back over here and said that I'm looking for a normal vector, I'm going to also have a plus or minus there to kind of signify that idea of like, hey, remember to just think about your answer when you're done, because it may or may not be the one that you end up calculating. So let's come over here and think about this vector that we just found. So we're looking for outward pointing normal vectors, which means if I come up and look at this shape and maybe find an outward pointing normal vector to that point, I think that that's the outward direction along there, right? It's going to point effectively from the z-axis straight out the edge of this cylinder, which means since it's pointing from the z-axis, because that's this thing is rotating around, I don't really expect my x position to change anything about the normal vector. And I can't quite tell if I just said z before I said x or not. If I said z, I didn't mean to. This thing is expanding along the x-axis, so I'm expecting that my normal vector will not have any dependency on x, which is exactly what we got when we calculated it. The x component of the normal vector was 0, which I think kind of lines up uh, with just stopping to think about the shape for a minute. Now, outward certainly makes sense if I'm looking at the picture and I can just draw a vector that points out. But as far as an equation goes, maybe that warrants a moment's consideration. So I kind of think that this outward pointing normal vector looks pretty similar to just the position vector, right? It's just the one that points, well, to the point. It goes from the x-axis to the point instead of from the origin to the point, but it still basically does that. So if I were to just naively pick a normal vector, just by looking at it, I think my normal vector might just be 0, y, x, because I just wanted to have a vector that gets directed to the point that's on this surface. Y and x here being sort of uh, simple stand-ins for the y value and the z value of the point. And if I go back and check the calculation that we got, while also putting my parameterization on screen in that upper left corner, I get -3 cosine t for y and -3 sine t for z, and my parameterization was 3 cosine t for y, 3 sine t for z. So I'm thinking that that also makes sense as well. But if I wanted to point out, I think I want both of these values to be, or both of those coefficients to be positive. Sine and cosine will take care of making it negative when I'm pointing in a negative direction. But I think I want the coefficients to be positive. I think I want the coefficients to match the surface equation that I had, which again was 3 cosine t, 3 sine t. So I'm going to use all of that to argue that n should be equal to 0, positive 3 cosine t, positive 3 sine t. And that that is going to be my outward pointing normal vector. So this one is outward. And if I again use some magic of copy and paste, I'm going to change this to gray and say that if I add negatives back in to each of those components, I now have the inward pointing normal vector. But again, we wanted the outward pointing one, so we'll go with one that has the positive coefficients. All right, and finally, the last part. Equation of the tangent plane to the surface at the point 1, -3, 0. Well, this time I'm given my point, but I don't yet know what my parameters are, s and t. And I already know that my normal vector doesn't depend on s, so I really just need to find t. Could find both though. I think I can see right away that s is going to be 1 because s is just equal to x. But again, won't super need that. I'm going to instead focus on the y component. I know that the y component of my point is -3. And from my surface equation, I know that the y component was 3 cosine t, which means my angle is pi. Right? If cosine t is equal to -1, then my angle should be pi. And that's going to get me a normal vector of 0, -3, 0. I wrote that down with the normal vector off screen, but I want to plug in pi for t into that normal vector that's there in the upper right part of the screen. So 0 is 0 for the x value. We knew that that wasn't changing at all. But then cosine of pi is -1, which is where I get 3 times -1 is -3. And sine of pi is 0. So I came up with a z coordinate or a z component of 0. So now I just need to plug all that stuff into the equation of a plane. So I'm going to get 0 times x minus 1 minus 3 times y plus 3. Y minus -3 becomes y plus 3. And finally, plus 0 times z minus 0. Z minus 0. All of that is equal to 0 because that's the equation of a plane. Again, I'm writing in a bunch of extra steps for emphasis so you can see how this plane was constructed. In the end, though, I am going to simplify this one and just call it y equals -3. Because I also want to argue that this plane should make sense. If I back up to my cylinder, I know I've got the point 1, -3, 0, which is over here on the back of my cylinder. That's the point that I'm looking to be tangent to. And if I'm all the way on the back end of that cylinder, I should have a vertical tangent plane. And again, shouldn't have any dependency on x. X can be whatever it wants. If I want this thing to be vertical, that means y equals -3 is a pretty good equation for a plane. That thing will stand straight up because it doesn't matter what z is. Won't change the number. So y equals 3, again, I think is going to be a pretty good plane. The line y equals 3 might just look like that if I'm fixing z to be 0. And then I could, maybe extend my plane up a little bit, sort of see this plane, and could also go down with said plane. So again, I think that's a pretty good tangent plane. But with that, I can put myself out, or I can, no, I don't know what analogy I was going to try to use there. Uh, that's the end of the notes that are here. I bet I went over the standard 50 minutes. So, I mean, no one was here to stop me. So I did what I want. Anyway, hopefully you found that helpful. I am going to end it here and I'm going to end the video here. And I will see you guys in lecture again soon. Okay, bye, 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 bye.